Hey everyone, this is Mrs. Drieski here. Today we are going to talk about the ratio test for convergence. But first, before we begin, I wanted to go over a couple of skills that we've learned in the past that we're going to need to know for today. So first things first, factorials. So just remember that n factorial is the same as n times n minus 1 times n minus 2 times n minus 3, and so on and so forth until we get down to 3 times 2 times 1. So if we had something like n factorial divided by n plus 1 factorial, what we could do, is we could expand out our numerator and denominator in this manner. And what you can see here is that eventually the n minus 1s are going to cancel out. The n minus 2s will also reduce and make a giant 1, and everything in between until we get to 3s, to 2s, to 1s. Even our n's are going to cancel out. Do you see that? Now, this doesn't leave a 0 in your numerator, obviously, leaves a 1. And down below, we've got n plus 1, so this can actually reduce down to 1 divided by n plus 1. Now, let's also review some of our exponent rules. So if we have something like 2 to the n plus 1 power, remember when your bases are the same, you can add your exponents. And we could go backwards so that if our exponents are added, we can replace it so our bases are the same. You might be like, well, where did the 1 go? Well, it's right here, silly. So if we've got 2 to the first power times 2 to the nth power, that's the same as 2 to the n plus 1's power. And so if we have a problem like this one, where we've got 2 to the n plus 1 divided by 2 to the n, we can expand out the 2 to the n plus 1 so that it looks like this: 2 to the first power times 2 to the nth power, all divided by 2 to the nth. And our 2 to the nth powers will cancel out, leaving us with a final solution of 2. Okay, so these are two of the skills that we're going to need for today's lesson. I hope that that was clear. Now let's go on to the ratio test. This is definitely my very favorite test for convergence. So what you're going to do is you're going to take the absolute value of a sub n plus 1 divided by a sub n, and you're going to calculate the limit as n goes to infinity. Now, if your result is less than 1, remember it's going to be positive, but because we're taking the absolute value. But if it's less than 1, then your sum or your series is absolutely convergent. Awesome. If it's greater than 1, then it's divergent. Now, if it equals 1, then the ratio test is inconclusive and you're going to have to try another test. So I hate getting 1 when I use the ratio test, because then I have to try something else. But it's fantastic for these other two cases. So basically, it's just substituting in an n and an n plus 1, oh good gracious Mrs. Drieski, into the series function, and then you're going to take the limit of the quotient. The value of the limit is going to help you determine the convergence. So here we go. This is example number 5. We're continuing on our second day of work on convergence tests for infinite series. So we are asked here to test this series for absolute convergence. So let's check it out. I've got blue. Step number 1, we're going to find a simplified expression for the absolute value of a sub n plus 1 divided by a sub n. So I'm going to go ahead and do that first. So that's my step 1. I do like to write down my steps. Keeps me organized, you know me. So I've got to calculate a sub n plus 1. Okay, I'm going to substitute an n plus 1 everywhere I see an n in this original. So that's going to give me negative 1 to the n plus 1 power multiplied by, now this is an n cubed, so that's going to turn into a n plus 1 cubed. divided by 3 to the n plus 1 power. Oh my goodness. Now this whole thing is just me substituting in an m plus 1 everywhere I see an n. That's just the numerator here. Now I need the denominator. It's the plain old a sub n. I'm going to need to make my absolute value symbol larger. So I'm just going to rewrite the original. So that's going to be negative 1 to the n power times n to the third power divided by 3 to the n. Good gravy. We're going to need to simplify this. So this is essentially a complex fraction, and I can break it apart. So let's do that. Negative 1 to the n plus 1 power, using my exponent rules that we just went over, starts with negative 1 to the nth power times negative 1 to the first power. Then we've got n plus 1 to the third. Okay. You know what I'm going to do? I'm going to just go ahead and expand my little division bar here so you can kind of see that this is a complex fraction, a fraction divided by a fraction. And one way we do that is we multiply by the reciprocal. So if I multiply by the reciprocal here, 3 to the n would be on top. So I'm going to multiply it by 3 to the n. All divided by, now I'm going to stretch this guy out. This is 3 to the power of n plus 1. So that's going to be 3 to the power of n times 3 to the power of 1. And if I'm multiplying by the reciprocal, this guy's going to be in the denominator, multiplying by this denominator. So I've got negative 1 to the power of n times n cubed. And if you recall in class, sometimes we would show that we're multiplying the top and the bottom together, and then we multiply the middles together. That's going to give your denominator. Oh, did you guys see this? These are going to cancel out. I love the ratio test. And let's see. Ooh, I got a 3 to the n power on top and bottom. That is also going to reduce. Let's see what I have here. So I've got the absolute value of, well, negative 1 to the first power is negative 1. But we're going to take the absolute value anyway, so that's going to become a positive 1. I can just drop that bad boy. And then I've got n plus 1 to the third. All right. All divided by, now in my denominator, I've got 3n cubed. Oh, this is interesting because I noticed that on the top and on the bottom, I've got terms that are being raised to the third power, right? So let's rewrite this so we can really see it. It looks like I've got, let's call it 1/3, right? Because we've got a little invisible one here, or when we took the absolute value, we could put it in, times, then I've got n plus 1 divided by n, all raised to the third power. We've used this skill before. When we notice that the top and bottom are both being raised to the same power, we can combine them together as an individual fraction that's being raised to that power. Okay, well, this is pretty good, but I do know that the next step for step 2 is going to be to calculate the limit to infinity. So in order for me to do that, I'm going to have to simplify this a bit more. So how about I have a dividing by n party? I'm just going to divide by n in this fraction though. It's basically going to be like multiplying by 1 over n. So I've got 1/3 times n divided by n plus 1 divided by n divided by n divided by n. Ooh, let's expand my parenthesis. All to the third power. Of course, the reason I did that is not because I want to make life difficult for myself, because I wanted to simplify some more. If we divide everything in here by n on the top and on the bottom, it's essentially like I haven't changed anything at all. Let us simplify this some more. And I get the absolute value of 1/3 times 1 plus 1 over n cubed. Obviously, n divided by n is 1. I could put it to a denominator of 1 if I wanted to, but it is not necessary. I think we are ready to apply the ratio test. So at this point, we have just been simplifying. Now we are going to apply the ratio test. This is step 2. All right, step 2 is just calculating the limit to infinity for the expression. So we're going to take the limit as n goes to infinity of the absolute value of 1/3 times 1 plus 1 divided by n to the 3rd power. Now, when I calculate the limit as n goes to infinity, the absolute value stays, the 1/3 stays, it doesn't have an n, 1 stays. Now, as n approaches infinity, 1 divided by n is going to go to 0. And we raise that to the 3rd power. Now, 1 plus 0 is 1. 1 to the 3rd power is also 1. And 1 times 1/3 is, 1/3. The absolute value of 1/3, 1/3. We are finally ready for step 3. Step 3 is just comparing to 1. So what is 1/3 compared to 1? Well, it's smaller. If the value is smaller than 1, then we're absolutely convergent. So the sum to infinity of that a sub n, which was, -1 to the n power times n cubed divided by 3 to the n, is absolutely convergent by the ratio test. The ratio test is especially useful when our a sub n is involving an n factorial or a constant being raised to the nth power. So this one had a constant being raised to the nth power. So that was how I knew the ratio test might be a good way to go. Although I like using the ratio test any chance I get. So maybe try this one on your own. I have faith that you guys can definitely do this. Again, you're going to start off by simplifying the expression for the absolute value of a sub n plus 1 divided by a sub n. So pause the video and try this one on your own. And if you get stuck, go ahead and push play. Did you guys do good? Here's how I solved it. So my first step was to simplify my a sub n plus 1. In this case, it's a k, so that'll be k plus 1. Oh no, it's a new variable. That's all right, you got this. Plug in a k plus 1. Everywhere we see a k. And then we're going to divide it by a sub n, or in this case, a sub k. So that's just the original. And now we're going to expand and divide. Of course, dividing is multiplying by the reciprocal. You could try Mr. Rainey's rule. -3 to the k plus 1 power is -3 to the k power times -3 to the 1st power. And this is getting multiplied by k plus 1 to the 10th. And since we're multiplying by the reciprocal, I'm going to take this 10 to the k and multiply that as well. All right, now it's time to divide. And we are going to expand these two. When we multiply by the reciprocal, this part is going to end up in the denominator. And this is already in the denominator, so I'm going to expand that exponent out. So I got 10 to the k power times 10 to the first power. And we've got negative 3 to the k power and k to the 10th power. Fantastic. Ooh, let's finish that absolute value. Okay, so look for the things that can reduce. I've got 10 to the k. That is going to reduce for sure. Negative 3 to the k power. That is also going to reduce. But I declare I think that is all we can reduce. So let us move on. Here we go. I've got the absolute value of negative 3 times k plus 1 to the 10th, all divided by 10 times k to the 10th. Oh, I love that. Do you guys see it? These both are being raised to the 10th power. So I can simplify this a bit more. I've got my negative 3 tenths, right? Times, since they're both raised to the 10th power, I can write them as a fraction. K plus 1 divided by k, all to the 10th power. Ooh, that looks like a 16. It's a 10. Oh my goodness, Mrs. Ryeski. Okay, now it looks like an 18. I give up. No, I don't. I will not be defeated by a 0. Success. Okay. It's the little things, right, guys? So I've got negative 3 to the 10th power times, I can simplify this some more because you know a limit is coming up. So that is going to give me, let's have it dividing by k party now. Divide each of those terms by k. Well, that's going to be nice. We reduce, and finally we have the absolute value of negative 3 tenths times 1 plus 1 divided by k to the 10th power. Wow, what an absolute value. Here we go, step 2. Step 2 is where we take the limit. So let's take the limit as k goes to infinity of this beautiful absolute value that we have just simplified. So when we do that, the absolute value of negative 3 tenths is going to stay. I haven't applied the absolute value yet. We know that's going to become positive, but I'll save it for our last bit. And then 1's going to stay the same. But when we take the limit here, as k gets bigger and bigger and bigger, this fraction's going to go to 0. Raise it to the 10th power. You got to love raising 1 to the 10th power. It's just 1. And then 1 times negative 3 tenths, you got that negative 3 tenths. Then take your absolute value. You've been waiting for that since the beginning. That is 3 tenths. And now we are ready for step 3. Step 3 is the part where we get to compare it to 1. So let's take 3 tenths and compare it to 1. Well, 3 tenths is less than 1. And if we get a result that's less than 1, well, my goodness, we have just shown that it is absolutely convergent. So we could say, therefore, the sum to infinity of negative 3 to the k power times k to the 10th, all divided by 10 to the k, converges absolutely. By the ratio test. Yay! All right. So let's try this next one. Here we go. Example number 7. Ooh, factorials, exponentials. This is a good one. Okay. Oh, I'm excited. So we're going to use the ratio test to determine if this thing converges or diverges. And then they also give us a little piece of information that's probably going to help us out later, that the limit as n goes to infinity of 1 plus 1 over n to the nth power is equal to e. Ooh, the natural base. So this is probably going to help us out in step 2, I'm guessing. So first thing I'm going to do is try and find the absolute value of a sub n plus 1 divided by a sub n. So I'm just going to substitute in an n plus 1 everywhere I see an n. So this is going to be n plus 1 factorial divided by, n plus 1 to the n plus 1 power. Fun. All right, down below is just going to be the original. So that's going to be n factorial divided by n to the n. All right, now I'm going to go ahead and break apart the exponents as I find them and take care of the division, I think. So up on top, I have n plus 1 factorial. And down, then that's going to get multiplied by n to the nth. All divided by, this will be n plus 1 to the n plus 1 power times n factorial. Okay, I can break apart this exponent a bit and I can try and stretch out my factorials. So let's do that. I like to stretch the factorials out. Okay, so that's going to be n plus 1. And then you just take away 1 here. So that's going to give me n factorial. And then we've got n to the nth. Down below, I'm going to break apart these exponents. That's going to give me n plus 1 to the nth power times n plus 1 to the first power. You can make your 1 visible or invisible, that's up to you, times n factorial. Let's extend our fraction bar. I can see some simplifying I can do right away. These n factorials, bye. And n plus 1, this n plus 1 is n plus 1 to the first power, as is this one, so they will also reduce to 1. And this leaves me with the absolute value of n to the nth power divided by n plus 1 to the nth power. Do you see it? Do you see it? My numerator and my denominator are both being raised to the nth power, so I can combine them together into one fraction where the whole thing is being raised to the nth power. And this is going to be easy for me to simplify because if I multiply the top by 1 over n and the bottom by 1 over n, then I haven't really changed the value of this. So that is exactly what I am going to do. I've got n divided by n divided by n divided by n plus 1 divided by n. That's a lot of dividing by n. And then we're raising it to the n power. All right, my n's are canceling out, and this is going to leave me with the absolute value of 1 divided by 1 plus 1 over n, and the whole thing is being raised to the n power. Do you know what time it is? It's time for step 2. So here we go. Let's go ahead and take the limit as n goes to infinity of the absolute value of 1 divided by 1 plus 1 over n, all raised to the nth power. Okay, so let's take a moment and recall that we were given this piece of information. And look at it closely. Do you see how this is actually our denominator? If we're calculating the limit as n goes to infinity of this piece, that equals e. So down here, we know that the limit as n goes to infinity of 1 plus 1 over n raised to the nth power is e. The only thing to note here is that it is in the denominator. So, and you know 1 to any power is still 1. So we're going to get the absolute value of 1 divided by e. Remember, the limit as n goes to infinity of 1 plus 1 over n to the nth power is e. Well, the absolute value here is just 1 divided by e. I love the natural base too. Step 3 it is. Now all we have to do is compare it to 1. 1 divided by e is what to 1? Well, 1 divided by e is, let's see, I'm going to pull out my trusty calculator. It is 0.3678, blah, 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 blah. So 0.37. 0.37 is less than 1. Therefore, the sum to infinity of our series n factorial divided by n to the nth power absolutely converges. Woohoo! All right, we have only one more left and then we'll be done here today. So let's go ahead and check out example number 8. We are going to use the ratio test to determine if this sum converges or diverges. So as usual, we're going to start with step 1 and find the simplified expression for our quotient. So here we go. Absolute value of, that just means I'm going to substitute in an n plus 1 to the original first. So I've got 2n here, so that is going to give me 2 times n plus 1. And then we're taking the factorial. It's going to be real important that you're careful with your parentheses in this problem. Then the denominator, we've got n factorial squared. So it is n plus 1, which is the factorial, and then the whole thing is being squared. And then of course we divide it by the original, so that is 2n factorial divided by n factorial squared, and the absolute value. Okay. Ooh. So I'm going to do my division step. So I'm going to multiply by the reciprocal. This is going to give me the 2 times the quantity n plus 1 factorial times n factorial squared, all divided by, let's see, the quantity n plus 1 factorial squared times 2n factorial. Ooh, this is going to be a fun one to stretch out. I'm excited. Here we go. So let's go ahead and do that. I'm going to do the distributive property. You know how I feel about that. So I'm going to distribute that guy so that then I can expand the factorial. And I'm going to write this guy twice. Let's see how that works. So I have, let's see, 2n plus 2. Now I could do the factorial here, or I can expand it out. So I'm actually going to expand it out. So I'm going to go 2n plus 1. So you just subtract 1 each time that you need to expand out your factorial. Then you're going to have 2n factorial. Now I stopped here because I had a 2n factorial in the denominator, and of course I'm hoping that I can cancel those out. And then I've got my n whoa, I said n, I wrote 2, goodness me, n factorial squared. Alrighty then, down in the denominator, I've got n plus 1 factorial squared. So that's like saying n plus 1 times, I'm going to expand that factorial a bit, so that'll be n factorial squared. Ooh. And then we have 2n factorial. I thought I was going to write it twice, but then I saw that I had this here. So I'm going to go ahead and reduce my 2n factorials. And this is a product, n plus 1 times n factorial, and that product is being squared. So just like a little aside here, if I have 3x that's being squared, we know that that's the same as 3 squared x squared, right? So that's the same situation that's here. Both n plus 1 and n factorial are being squared. So I can make sure that I'm squaring each of these factors. So that's my next plan. I've got in my numerator, I'll go ahead and 2n plus 2 times 2n plus 1 times n factorial squared, all divided by, and this is going to give me, let's see, n plus 1 squared, n factorial n factorial squared. Now, of course, I hope you see why I just kind of giggled a bit, because I see that the n factorial squareds will reduce now. We don't need this anymore, huh? Okay, so up in the numerator, I see, well, let's just go ahead and keep going here. I've got the absolute value of 2n plus 2. I'm thinking I'm probably going to need to factor this out in a minute. And then I have 2n plus 1. And down below, I've got n plus 1 squared. Well, that's the same as n plus 1 times n plus 1. Oh, yeah. Now, 2n plus 1 will not cancel out an n plus 1. But since this guy now has both terms that have a 2 in them, they're both divisible by 2, I can factor that out. I multiplied it through so that I could do that factorial nicely, but it doesn't have to stay there forever. Lovely. So I can get these n plus 1s to divide and make 1, leaving me with the absolute value of 2 times the quantity 2n plus 1, all divided by n plus 1. Are we ready to ratio test yet? No, I bet we can simplify this some more. I'm going to extend it out over here. I'm going to use the distributive property. I love it. I'm going to use it. This is going to give me 4n plus 2 divided by n plus 1. And you know what? I think I'm ready for a dividing by n party. My highest power of n is a first power. So if I divide every single term by n, I'm going to be able to take a limit easily. So this is going to be 4n divided by n plus 2 divided by n divided by n divided by n plus 1 divided by n. It is a dividing by n party. So these n's will cancel out. So these ones go away, these ones go away. And I get the absolute value of 4 plus 2 divided by n, all divided by 1 plus 1 divided by n. I think it's a ratio test time. I think that's about as simple as I can get. step 2, I know, step 2 after all this work. Step 2 is where we take the limit. So the limit as n approaches infinity of the absolute value of 4 plus 2 divided by n divided by 1 plus 1 divided by n. Well, as n gets larger and larger, 4 stays 4, but 2 divided by n becomes 0. 1 stays 1, but 1 divided by n becomes 0. I'm getting the absolute value 4 divided by 1, which is the same as 4. Now it's time for step 3. Step 3 is where we compare it to 1. 4 compared to 1. Well, 4 is larger than 1. If this is the case, if the value that we get at the end after taking the limit is greater than 1, this tells us that it's divergent. So this series diverges. So, therefore, the sum to infinity of 2n factorial divided by n factorial squared is divergent. So they don't always absolutely converge. And that, my darlings, is what I've got for you. I hope that it made sense and that you enjoyed the ratio test as much as I do. Please make sure that you go back and watch the other convergence tests in this series if you still have questions about them. But this concludes day 7 of our convergence tests of infinite series, part 2. Go ahead and do that homework assignment on My Lab in Mastering. And if you'd like, there's some extra practice in our textbook. You can do that as well. Goodbye. I hope you guys are having a great week, and I'll talk to you soon. See you later.